see this later, they can. Okay, so for the determination of the concentration of unknown silver nitrate solution, right? You see this one? Okay. So for the following problem, we have a given reaction, right? Sodium chloride reacting with silver nitrate will form this, with silver chloride being a solid. Okay, so it says blah blah blah, all of this, silver chloride is a solid. The solution labeled solution 3 is an unknown amount of silver nitrate. We want to design and perform an experiment to determine the mass of the silver nitrate that's in solution 3. So here's solution 3, right? If I click on the solution, it tells me some information about it here. I have some other. Now, did you remember what's in solution 3 here? What is the unknown in there?
It's an amount of silver nitrate.
That's right, silver nitrate. So what compound would I want to put in there to perform this chemical reaction up here? I have the silver nitrate in the Erlenmeyer flask already.
Right.
I need to add the sodium chloride to it if I want to perform this chemistry, right?
Okay.
You see that?
Yes.
So I'm going to choose the sodium chloride. Now, this one's pretty straightforward because if I go like this and add masses of sodium chloride into here, let's say I add 0.01 grams and I just pour it in. Then when I click on this, it tells me how many grams of what? What is it telling me? Grams of what here? Can you see that, Samantha? Are you still there?
You are currently the only person in this conference.
I am so sorry about that.
Are you there?
Yeah, I'm back. My computer freaked out and shut down, and it was a mess.
Well, that's fine. I'm just glad that it wasn't on my side because I thought, oh no, everybody's trying to get on, but they can't. All right. So, ready to go again?
Yes.
All right. Okay, so here we have our solution of sodium nitrate. We added the sodium chloride. We've added, how much did I add? 0.1 grams, I think it was. And it says here that, whoops, if I click onto here, it says that I have 0.0245243 grams of, what is that? You see that?
Yes. Silver chloride.
Silver chloride, right? So it tells me how many grams of silver chloride I made, right, following the equation up here, by adding a certain amount of sodium chloride. So if I keep adding more sodium chloride, let's put some more in. Let's put another 0.2 grams in this time, right? And I can see that the silver chloride mass increased, right? Now, why is more silver chloride being produced in this bottle when I add sodium chloride?
Because more chloride is becoming available to react with
That's right.
the silver.
With the silver ion. That's right. So we're getting silver chloride here. All right. So what happens if I put 20, or let's just put 5 grams? What happens if I'm going to put 5 grams in there? Will I get more sodium or silver chloride?
You might, but it also might run out of silver to react with.
That's a good point. Right. So let's put it some more. Okay. So I got more, 2.21. Let me put in another gram, okay, and see what happens this time. Okay, so I put it in. I clicked it, and I can click it a couple more times, see? But it's not increasing. Why isn't it increasing now?
It's run out of silver to react with.
That's right. So now this is how many grams of silver chloride I have in my vessel. And the mass of silver chloride there, I can convert to moles of silver chloride. And from that, I have a molar ratio of 1 to 1. I can know how many moles of silver nitrate there must have been in my sample. And I can convert that to grams of silver nitrate. Does that make sense?
Okay. It does. So you didn't have to set up a burette and a titration for this one?
Nope. Nope. You don't have to do, I mean, all of them are a little bit different from each other. But
Okay.
you can do whatever you need to do to solve the problem. Does that make sense?
It does.
All right. Should we try to get a second one? Look at a second one here?
Sure.
All right. The second one here is our acid-base titration. All right. Now this one says, determine the concentration of an unknown acid solution using sodium hydroxide and solid KHP. Has some instructions here. Using the virtual laboratory Design and perform an experiment to determine the concentration of the unknown HCl. Let's look at the bottom here. So it does want us to know the unknown concentration of HCl and write the answer here, right? See that?
Yes.
So that's what we're after. To 4 significant figures, the concentration of the HCl and NaOH are about 0.1 molar for the HCl, 1 molar for the sodium hydroxide, respectively. Solid KHP is provided. Please fill out the feedback form below when finished. So we don't have to do the feedback form, but we don't have to do that, right? Did you get to look at this one already by chance?
I did, and this is the one that I was really confused about.
Okay.
I thought you had to set up a titration, but I couldn't get things to come out of the
Out of what?
burette. The burette, I could
Oh.
pour things into it, but I couldn't get them out.
Okay. So here I brought out a burette for us, right?
Mhm.
What are we going to put in the burette? Should we put some sodium hydroxide? Is that okay?
HCl, I think.
You want to put the HCl in the burette? And what are you
Is
going
that how
to...
it goes?
Well, it just depends on what we want to get done. So
Ah,
first, how are we going to determine... Do you know what the KHP is? Did you look into that and see what that was yet?
is that the indicator?
No. So let's look up KHP. I'm going to go into Google here and look up KHP in titrations. All right. So KHP is a commonly used primary standard for titration with sodium hydroxide solution. It's the weak acid hydrogen phthalate, KHP. In this reaction as well, 1 mole of KHP completely reacts with 1 mole of sodium hydroxide. The titration of sodium hydroxide with KHP involves adding sodium hydroxide from the burette to a known volume of KHP. So we can click on here to learn a little bit more. But what this looks like here, that's not the KHP, right? Let's see. Where's the KHP? Do you see KHP? Here it is. Here it is. The primary standard. This is KHP right there. So there's the chemical reaction. This is KHP. Reaction between KHP and sodium hydroxide. So it looks like it's a 1-to-1 ratio. And KHP is a material that we can use to identify the concentration of sodium hydroxide. Can you see that from this information here?
I can. Okay.
Okay, excellent. So then, it looks like we want to determine the concentration of the, well, so the KHP is to determine the concentration of the sodium hydroxide. If we looked into it more, well, I mean, maybe you can realize. Do you have any ideas what we might have to do then with the KHP? How would we incorporate the HCl into all this? Any ideas?
We'd use the KHP first and then figure out the concentration of the NaOH, and then we'd do it again using the HCl.
We'd use the NaOH to determine the concentration of the HCl, right?
Yes.
Right, very good. So, if I got a little flask here, whoops, that's not what I wanted to get. If we get a flask, glassware, there we go, Erlenmeyer flask. Get a flask here. And then let's put in an amount of KHP into this flask, okay? Now, I don't know if you messed around with this scale or whatever, but you can get the scale and you can put stuff onto here. But I also found that if I just go like this, I can pour exact masses, precise masses, just like that. Does that make sense?
It does.
So I'm not going to have to use the scale because it pours precisely for me. But maybe we should do a calculation to determine how much KHP I should put in here. Or do you have any ideas how we could determine how much KHP I should put in there?
If we were to do a calculation, then
What would we want to know?
we already know that it has a 1-to-1 molar ratio with the NaOH.
Yeah.
Um,
What question would we like to know here? How many grams of KHP? Is that right?
yes.
Okay. So what could I start with?
Start with grams of NaOH. Do we know that?
Okay. Well, our NaOH is a solution. True.
It is. That's right.
So let's see. Have you opened up one of these? Have you opened up one of these for yourself? One of this thing? Can you see my screen now?
I can see your screen now. Currently, I can't run this tab and that at the same time without my computer crashing.
Okay. Well, we'll just have to do it on my computer, and I'm recording this. Am I still recording this? Yeah, still recording it. So when you go back, you can watch it again if you forget something, okay?
Okay.
All right. So then our sodium hydroxide here is about 1 molar. And if we did a titration with sodium hydroxide, that's about 1 molar. If I get the other solution, the HCl solution, it's about 0.1 molar. So if we did a titration of this HCl with this sodium hydroxide, we want our volume that we titrate to be more than 10 milliliters, because if it's less than 10 milliliters, then our precision isn't going to be very good. Right? You remember we were talking about that in lab?
I do.
So we want to dilute this sodium hydroxide down before we use it in our titrations. So let's do that first. So I'm going to get another Erlenmeyer flask here. Actually, might as well get a beaker, it doesn't matter. I get a beaker here, and I'm going to dilute it down to about 0.1. So right now it's 1 molar. I have a 250 milliliter beaker. So if I put in here 25 mils, okay, and then if I want it down to about 0.1, what do I have to do now?
You'd have to do 75 milliliters of water.
75, or let's see, I added 25 and I want it down to 0.1, so that's 1/10. So would I need to fill it up to 250?
Yeah.
Is that 1/10? So how much is 20? So 175, is that what you said? No, wait. 200.
I said 75, but
225, right? 250
right.
minus 25, okay. 225. So I'm going to add 225 water. Now this is 0.1 molar. I'm going to get rid of this water and make some space here for us. So this is 0.1 molar sodium hydroxide, or about 0.1 molar sodium hydroxide. So I'll put that into my beaker here. I'll put in 52 milliliters. Fill it up to the 0. So that was nice and easy for us. And now I would like this titration. Let's aim for maybe 20 mils. We'd like the titration to require 20 mils. So that's information that we can use in our calculation, right? So let's go back to this here. So if we want to use 25 milliliters of our sodium hydroxide solution, right? All right, and then actually, instead of writing 25 milliliters, I'm going to change this into 0.025 liters. Is that okay?
Yes.
All right. And then I can get liters of sodium hydroxide down here. Right? And where am I going to want to go to from there?
To moles.
To moles, right. like 0.1, right? Because that was the molarity that we pretty much have, right?
Right.
That's moles of sodium hydroxide. Okay, so moles of sodium hydroxide, I want to go to moles of KHP, true?
Yes.
All right. Moles of sodium hydroxide down below, moles of KHP up here. Do you know the molar mass of KHP?
I don't know the molar mass. I know they had a ratio of 1:1.
Yeah, that's
I'll
good.
look it up.
So that's 1 mole of KHP, 1 mole of sodium hydroxide.
And the mass is 204.22 grams per mole.
4.22 grams of the KHP, right?
Yes.
Okay, do you have a calculator? Figure that out?
Yes.
There's a P there. What'd you get?
0.5105.
0.51, huh?
Yes.
Excellent. So let's go to our back to our titration setup here, and let's add that mass of KHP into here. 0.5. I'll just do 0.5 to keep it easy for us. Is that okay?
Yes.
Okay. So I'm going to put it in there. There we go. We got 0.5 of KHP in there. I think we're going to need some water in here. So I'll get some water. How much water do you think I should put in? Does it matter?
How dilute do we need it to be?
It actually doesn't matter, right? Because the amount of water isn't going to change the overall number of moles of KHP. It would dilute its concentration, but that's not going to change the reaction because the sodium hydroxide is still going to react with the same material. And that's an interesting thing about titrations. It doesn't matter the volume of water that you add with your reagent. The only reason you add water is just so, first of all, you want the solution to be aqueous so the materials are available. And usually when you're in the lab, you don't want things to splash around, so you add enough water. So let's just add like 25 mils of water, okay?
Okay,
Does that make sense?
it does.
All right, so here I have my KHP and my water, and we're going to standardize the, I already added this in, I'll keep it over there. Whoops, nope, I want to move it over here. I'll keep it over there. And now we're going to standardize our sodium hydroxide. Is there something I'm forgetting? Anything else, or are we ready to start?
If this were in a lab, we'd be stirring it, but I couldn't find a stir bar.
That's true, but you're right, we don't have a stir bar. In our labs, we did have a stir bar. In the olden days, when not everybody could afford a stir bar, you would just use your hands and swirl the titration as you performed it. But that's a good point. But there's one other thing that we have here in our solutions column here that we need to add. What is it?
The indicator.
The indicator. No indicator, we don't know when the titration ends, right? So I'm going to put maybe about a milliliter of the indicator into there. There we good. Okay. I'll remove that and get that off the board for us. Now it looks like I'm ready to, and so this is how I put the burette into there. I drag it over there like that. Now I'm ready to deliver this volume here. Okay?
Okay.
So how many did we say it should take?
25?
25. So maybe I start just delivering 15 to speed things up. Is that okay?
Mm-hmm.
It didn't turn color, so I'm at 15. Now maybe I deliver in 1 milliliter, or maybe, yeah, maybe 1 milliliter. 16, 17, 18, 19, 20, 21, 22. Maybe I do 0.2 now. 23, 24, 25. I think I'm going to go down to 0.1. Is that okay?
Yes.
Nice and slow here. Now, do you remember at what pH phenolphthalein changes color?
Was it between 8 and 10?
Yeah, I think that's right. So over here on the left, you see it's telling me what the pH of my solution is. So that's kind of an indicator to help me know when I'm getting close to the phenolphthalein color change and the end point, right? Does that make sense?
That's cool.
Yes, that's helpful. So 7.71, we're changing pretty fast now. It's going to be changing really quick now. So I could even go down to 0.05, for example. Whoops, 0.05, there we go. And then I can just add little tiny bits at a time here. There it is, see that? It's already changed color, right? So what's the volume that I've added? Can you see it there?
26.6?
Yeah, 26.60. 26.60, all right? So, 26.60. Can you write that down for me so we don't forget? We don't have to keep going back and forth. Okay. So, 26.60. We're going to do another calculation, right? This time, we want to know what? What do we want to have at the right of our equal sign? What do you think? Why did we do that titration? What were we looking for?
To standardize our NaOH to figure out how much sodium was in it.
Sodium hydroxide. We wanted to know standardize the NaOH, just like you said. That means to identify its what?
Concentration.
That's right. And what are units for concentration?
Grams per mole?
No,
Grams per milliliter?
it's just molarity. Molarity, right?
Molarity.
Which is moles of sodium hydroxide, right? Moles of sodium hydroxide for every what?
Liter of solution.
Liter of solution. Very good. Okay. So I can start over here knowing that I had how many grams of KHP did I put in there? Was it 0.5, is that right?
Yes.
Okay, 0.5 grams of KHP. And what was the molar mass of KHP?
204.22.
Okay. 204.22 grams of KHP for every 1 mole of it, right?
Yes.
This is horrible. I hate this thing. 1 mole of KHP, and then we go from moles of KHP to what?
Moles of NaOH.
That's right. Hey, why don't you come on here and help me so we can speed things up? Zaf, you want to help out too? So we're going moles of KHP to moles of sodium hydroxide. Go ahead and write that in there. And then we need liters of our solution down here, correct?
Liters of solution. Okay. All right, just So, what solution are we on now?
Of the sodium
yes.
hydroxide solution.
So this is the NaOH, and to convert it,
Very good. So we have moles of sodium hydroxide up top.
we have to be moles over here too.
No, and this is going to be liters, and that's it.
Liters.
So we got
Okay.
moles per liter because that's what we're after, right? All right.
Aye.
So we got 0.5 divided by 204.22. Now, what was this, Samantha? Do you remember? You wrote that down for us?
26.6.
Is that
26.6.
milliliter?
That's milliliters, though, so
Okay. It should be converted to
0.0266.
0.026. Okay. You want me to help it out? Okay. Point. Okay. 266.
Very good. Now, it's not 0 point, though, right? It's 0.0, correct? There you go. One more zero in there. Very good. All right. Somebody do that calculation for us. Who's going to do it?
Okay. I'll do it.
Okay. So 0.5 divided by 204.22 divided by 0.0266. And that should be our molar concentration of sodium hydroxide.
Divided by 0.0266. So the answer is 0.09204. So 0.0920.
204, is that what you said?
Yes.
Okay. That is the molarity of our sodium hydroxide. Does that make any sense, Samantha, or is that too low?
I feel like that makes sense.
What did they say the concentration of our sodium hydroxide was supposed to be? Can you write that down for us, Samantha? 0.09204. Or just if you can write it down somewhere else so we can share my
gotcha.
screen and go off of her.
Yes.
0.09204.
Got it.
Okay. So what was our concentration of our sodium hydroxide, did they say about here?
1 molar.
So are we off or what happened?
We are off.
Or did we dilute it?
We diluted it. That's right.
That's right, we diluted it. So we're okay, right? It's about right. Because we diluted 1 to 10. Okay, very good. So now we know our sodium hydroxide solution. Let's go back to this. We're done with this. We can put it over there. Let's get another Erlenmeyer flask out for ourselves. And this time, let's put in about, we want our titration to take, again, about 25 mils. So how many milliliters of this 0.1 molar, or approximately 0.1 molar, HCl should we put in there, Samantha? How many mils should I add?
Would we do 25 again?
Yeah, why? Well, how did we know to add 25 into that flask? Because
That's what we did
it's
last
because it's very similar in terms of concentration, right? The concentration of this base we said was almost 0.1, and the concentration
Right.
of this acid is approximately 0.1. Okay, why don't I fill this thing up to 50 again if I add 26.6? So we're up to 0, is that right? Okay, I'm sorry I'm the only one having fun with the titration here. Am I ready to rock and roll?
Yes.
We need to add indicator to the.
Ah, yes, we need to add indicator. If we don't add indicator, it's not going to turn
Yeah.
color for us.
3 drops, right?
Yeah, or I can just put in about 3 mils here. Or sorry, 1 mil here. So pour it in there. Very good. Okay, so I'm going to remove this. I'm going to remove the KHP just because I'm feeling a little cluttered. I'll put this back by the sodium hydroxide. Okay, now we're ready to go. So I can watch the, I mean, we know it's going to take about 25 mils, right? So I'll add 10 to start off with. And I can see the pH didn't hardly change, 1.26, right? I'll add another 10, 1.64. Maybe if I add 5, 1.93. So maybe I'll add 1 milliliter increments for a while. 2, 2.2, 2.4, 2.6, 3.1. Oops. Ah! I went too fast. It happened between 31 and 32. Right? Did you guys see that?
Yes.
Okay.
Yes.
That was dumb. Okay, between 31 and 32. Somebody remember that. I'm going to remove this bad sample that I made a mistake on. Whoops. I'm going to get another flask. All right. One more time. 25 mils. What else? Phenolphthalein. Want some space here. Phenolphthalein. 1 milliliter. Where did it change? Oh, I removed the wrong thing. Come on.
No.
Sucking away our life. All right. 25. Do I have enough? Yeah, I do. Okay, good. 25. Phenolphthalein. 1 milliliter. Excellent. Get it over here. All right. Now, oh, I need to put some more sodium hydroxide in. About 32 it looked like, right?
Mm-hmm.
So, oh, that wasn't the sodium hydroxide, was it? Oh. Why was I not supposed to add that one, Samantha? You see?
That was the undiluted
It
one.
was the undiluted one. That's right. Did you know? Did you see I was doing it wrong?
No, I did not.
Okay, let's try again. This is our diluted stuff. This goes here. 52 mils. Okay. You go back over there. We're ready. How many do we have to add?
Between 31 and 32.
So I'll add 31. And then I'll go in 0.1 milliliter increments. I'll watch the pH over here. There it is. So 31.5. 31.5. So where are we at? We're going to go back to our calculation page now. All right, so somebody has this written down, right? So if we need to remember that, we can. Oh, we need it right now, actually, right? Because we need to, now to the right of our equal sign, we need to write. So let me see if I can. Erase all this. To the right of our equal sign, we need to have a what? What do we want to the right of our equal sign this time?
Moles of chloride.
Yeah, moles of HCl, right? Per what?
Liter of solution.
Liter of solution. What do we start with top left here, Samantha? Why don't you write it?
Is that the moles of KHP?
No, I think we know how many milliliters of the sodium hydroxide, right?
Oh, that's right.
Or you can write it in liters instead, right? Zaf, down here, you want to write liters of sodium hydroxide?
Oh, yes.
And we'll use the
Yes.
molarity to go to moles of sodium hydroxide.
Okay. Mm, Is that correct? The next line would be down here should be moles of sodium and HCl, or
That's
like
right.
the
Yep.
relationship between the two.
That's right. Go for it.
I haven't come across to this experiment yet. Still working on the
Sure.
unknown base. And should I refer to the given problem, like based from the equation? Is that where
Yeah.
I'm gonna get the
Mm-hmm.
data source?
So it's 1 to 1. Right here goes our molarity of our sodium hydroxide, Samantha, right?
Yes.
So you can write the molarity, moles per liter. Now we're in moles of HCl, and now we just need liters of HCl down here. Zaf, you want to do that?
Okay. So, pardon. Oh. Okay. So there should be the liters of
Yeah, of the HCl solution.
HCl now. Okay. We're on to the final answer.
Okay, very good.
Oh, solution. Okay.
Yeah, that's, helpful, but not necessary, obviously. All right, so Samantha's writing the molarity there. So we got the liters of NaOH, 0.0315, moles of NaOH, and then divided by the liters of HCl. Does anybody remember how many liters of HCl we started with?
26. Oh, the 0.026.
It was 25, wasn't it? Did I do 25?
Oh, the starting. Yes. Yes.
0.025 liters. That's right. So why don't you perform that math, Samantha, and tell us what we get.
Zero 0.1159.
Okay, 0.1159. So that's the molarity of our HCl apparently, huh?
Yes.
Okay, so let's go over to our answer here and see if we're right. So down here, what's the concentration of the HCl solution? It says 4 significant figures? I thought it was just 3. This one's 4, so it's 0.1159. Is that what we said?
11597. So I guess we'd round up.
11597. So
Yes.
60 then?
Yes.
Let's check and see if we're right. Yay, we got it.
Hmm.
So that was the concentration of the HCl. All right.
Oh, wow.
Very good. So, Samantha and Naf, if you come back and watch the rest of the video, we went through we went through silver nitrate determination and the acid-base titration, right? Were you working on, which one did you say, Naf?
I'm working on the unknown acid.
Unknown acid problem right here?
Yes.
Okay. Do you guys want to go over that, or do you want to try it on your own a little bit? Or if you're tired of doing this, we can stop, but if you want to keep going, we can keep going. What do you guys think?
Sure. We can keep going.
Okay.
Okay. Okay. Yes.
So
I'm
let's
down.
go to the unknown base problem. Is that what you said, right?
Unknown acid.
Oh,
But,
sorry.
Yeah, unknown base could be.
Unknown base, you said?
That works too.
Okay. All right. So your company has just purchased a. Wait, you said unknown acid, right? Is that what you said?
Yes. Yes.
With this one right here. Okay, so let's do unknown acid.
Okay.
Okay. So unknown acid problem. Your company purchased a warehouse and there's a bunch of acid around, and you need to decide this bottle that says acid, right? Here it is, unknown acid. It just says acid. We need to decide what? We need to know what's in the bottle. So these are our choices. And then we also want to know the concentration of that acid to 3 significant figures. Okay. Now, what did you get to look into it at all, Naf? Do you have any ideas?
Um, Actually, I don't know how to start with because I'm confused with is trying to find like actually from utilizing the tools. Yeah, that's our.
Okay. So let's go into Google here and say identification of an unknown acid. All right. Identification of an unknown acid. That's pretty good. Let's see what it says here. In this experiment, an unknown acid will be identified by titration with standardized base. Let's see. Did they give us some base in this question here? What do they give us? Yeah, they give us lots of different concentrations of sodium hydroxide. That's nice. Okay, so that looks like something we can do. The pKa values of the acid. The pKa values of the acid. Do you guys know what that means? pKa values of the acid. Here it does say pKa values, right? See that? So that's maybe helpful. And the molecular weight of the unknown acid. What is it? This titration data will be used to construct a titration curve for which the following information will be obtained. Okay. So, procedure, standardize your sodium hydroxide with KHP. Well, hopefully we don't have to do that. Let's see. Do we have to do that with this one? I don't think so because it's telling us the concentrations, right?
Yes. I have a question.
Yeah.
Why might the lab tools are not showing up in my? It's just the activity one, and then it's completely blank.
So you clicked on oh, okay. So where it says activity 1. Okay. So what's your browser?
It's Google Chrome.
Google Chrome. So in your can you see my page?
Yes. Yes.
Let's see, where are is it this one here?
Oh, okay. I just refreshed it. It showed up.
Did it? Okay. It has to do with the JavaScript, I think, working sometimes and not working others. But anyway, okay. Okay, so you still there, Samantha?
Yes.
All right. So what are we doing? What are we doing? What are we doing? We are trying to, we were trying to follow this as an example. Okay. So to determine, so this here is what happens when you monitor the pH, see the pH, versus the volume of base added in milliliters. See that? And you get this titration curve as follows. So if we monitor the pH as we add our sodium hydroxide, we get this curve. And this curve, if we were to keep reading through this, we would see that this curve allows us to identify the pKa. So notice, let's see, where is it? Which one of these talks about it? So maybe I open up another one that is a little bit. Finding the pKa of a weak acid. Okay. With a titration. Okay. Titration of a weak acid, finding the Ka using a titration curve. All right, this one's only 4 minutes. Let's see if this one makes any sense for us.
Okay.
Honey to save you hundreds of dollars this year and thousands of dollars over your lifetime. Here's how Honey works. This is 3,000.
Happy Halloween, guys. Trick or treat. Oh, you want a treat? Well, here, let me show you how to find the Ka of an acid from a titration curve. When you start with acid and you add base to the equivalence point. Now, the first thing is, if you're trying to find the Ka with a titration, you don't need to go any farther than the equivalence point. But maybe you did. I don't care. So, here we go. At the equivalence point, we have added just as much base as we have of acid. That's the definition for equivalence point.
Does that make sense, guys? Did you guys catch what he said was the equivalence point? Should I play that back again?
Okay.
Samantha, are you there?
I am.
Okay, great.
I can't hear the audio from the video, but I can see
Yes.
it.
You can't hear the audio. Oh,
Oh,
Yeah.
yes, that's right. I can't hear it too.
why can't we hear
Sorry.
the audio? Okay, so I will. Ready? Let's watch it again, and this time I'll talk for you. I'll talk for you. Okay?
Okay.
Well, here, let me show you how to find the Ka
Let me show
of an
you how to
acid
find
from a
the
titration
Ka
curve.
of an acid
When you start
from
with
a
acid
titration
and you
curve.
add base to
We're
the
starting with
equivalence
acid.
point.
We're adding
Now, the
base. We're
first
getting to
thing
the
is, if you're
equivalence
trying
point.
to find the Ka with a titration, you don't need to go
This-
any farther than
We
the
don't
equivalence
have.
point.
We don't need any of that
But
data.
maybe
All we
you
need
did.
is
I don't
where
care.
the equivalence
So,
point is,
Here we go.
and this is the
At
equivalence.
the
point.
equivalence point, we have
At that point,
added just as
concentration
much base as we have
of
of acid.
base that we've
That's
added,
the definition
or
for
the amount of
equivalence
base we
point.
added, is equal to the
What you'll
moles of
notice
acid
about
that we had to
titration-
start with. Does that make sense, guys?
It does.
That's why
Yes.
the pH is changing, and that's why our indicators generally change colors, because there's a broad range of pH that changes, and the indicator changes color in that region. So the end point, the equivalence point here, is the point at which the moles of base we added are equal to the moles of acid. All right?
Curve is that there's a buffer region here.
Halfway to that point
Notice about
is
the
what we
titration
call
curve is
our point of buffer, where our solution is half of the acid, because half of the acid has been consumed, and half of that acid is in the basic form because it's been consumed. So let me go back to this slide here, or no, this page here. Can you guys erase all your stuff that you wrote? The trash can there. Zaf, are you there?
Oh, yes.
If
yes.
you could use the garbage can to erase everything you wrote,
Oh,
is that-
okay.
or is that everything I wrote? You see the
I
little,
think that's
you see the little garbage can symbol there? There we go.
okay.
Excellent. So let me draw our own. Whoops, gotta get red here. Let me draw our own little titration curve. Okay. Whoa, that's thick. Let's get a thinner line. Okay. Here we're monitoring the pH. And what are we adding?
The K. Oh, no.
We're adding what?
Problem. Mm,
We're adding the sodium hydroxide, right?
yes.
Does that make sense, guys?
It does.
And the pH changes accordingly, right? We get ourselves a pH curve. At this point here, that's our equivalence point. And all of the acid, let's say our acid is HA. We're adding acid. It's combining with the hydroxide ion here, or NaOH. We could include the NaOH, but the sodium is just a spectator ion. And the products for this are H2O and the leftover anion, or A minus. So the hydroxide ion takes the hydrogen away and leaves behind an A minus. Okay.
I have a question.
Yeah.
Rather, is it true that the relationship between the acid and the base is always like equal? Like for whatever the amount of acid is, there should be same amount as the
base?
Yes, the base.
It depends on the acid, right? So some acids, it's a 1-to-1 ratio, and some acids, it could be a 2-to-1 or a 3-to-1 ratio. It depends. If it's let me draw a quick little curve here. If it's a 2-to-1 ratio, if there's 2 hydrogens on here for every hydroxide, then the titration curve would look like this. You'd have 2 bumps, one for each hydrogen that comes off. Does that make sense?
Yes.
Okay. So, when we get to this point, the end point, all of the HA is gone. But if we're only halfway to that point, so if we measure how much that point is, if we're only halfway, then, then that is called the pH that it is at that halfway point right there, is called the pKa. pKa. It's a special pH is what it is. It's the pH at which half of the acid has been dissociated, or half of the acid has been converted from HA to the A minus form. That's what the pKa is. So in this experiment, we can perform a titration and monitor the pH and see when the pH reaches these pKa's. And when it reaches these pKa's, then what we're going to see, then we're going to take the twice that value when that pKa is reached, and see if our endpoint matches up with it. Okay? So, let's see here. Let me get some glassware out. Let's get a Erlenmeyer flask. All right. I could get a, where is it at? There we go. Burette. What are we going to put in the burette? A base, right? Does it say it doesn't say the concentration of the acid, which is silly because we could check its pH and pretty much know its concentration. But let's see here. Does it say its pH? Its pH is 2.37, so it's not very high. So let's use a low concentration like 10 or 0.01 molar. Okay, so I'm going to put the 0.01 molar into here. 52 mils fills up these burettes. All right, now my burette is filled with this sodium hydroxide. Let's put in some acid here. How about 10 milliliters of acid? Did I do it? I don't think I did it. 10 milliliters of acid. There we go. And then, here we go. We're going to start our titration. Okay? As I titrate, so if I click on here, I see that the pH is 2.37. As I titrate, now there's a variety of ways I could do this, but as I titrate, what I'm going to do is I'm going to watch these pKa's as they come by. As the pKa comes by, that's an indication that the acid, or that's a point at which we might have reached half the endpoint. And then when we reach the endpoint, and we'll know we'll reach the endpoint because our pH will shoot up to past 7, about 8 or 9. when we reach that endpoint, we'll be able to know where the halfway point was. Okay? So I'm going to add, let's start off with just 1 milliliter of my 0.01 molar sodium hydroxide. Now they don't give us a indicator in this problem. Oh look, they did give us an indicator. I didn't know that. It's wonderful. Not that we need one, but we'll put one in there. Okay. Here we go. So as we reach our pKa's, we should stop and jot down the volume. And if the titration ends at twice the volume, then we know that that was the acid. Okay? So the first pKa is our methylmalonic acid at 3.07. So let's add this stuff until we reach 3.07. So I added a milliliter. I'm at 2.39. Whoops, I didn't add anything. Okay, there we go. 2.45. I added a milliliter. I'm at 2.45, 2.51, 2.57, 2.62, 2.69, 2.7, 2.75, 2.78, 2.8, 2.85, 2.91, 2.94, 2.99, 3.01, 3.03, 3.05, 3.07. So that's at 19 milliliters. All right? Yeah.
I can't see the virtual lab on your.
Oh, man. Why didn't you guys tell me?
Sorry. I just.
Samantha, are you there?
Yes.
You guys were just listening to me. You weren't. Maybe I'm making you go to sleep.
Oh, no. No, you're good.
I thought there was a reason you hadn't shared it.
Sorry about that.
Actually, I was trying to look for it. See how to remove the.
Okay. So what I've done here is I have my titration going. I put 19 milliliters of my 0.01 molar sodium hydroxide into here. Or sorry, put 50 milliliters. And now I've delivered the 19 of it, 0.01, into, how much did I put in here of my unknown acid? Let's see, there's 30 mils in here. What's 19 minus 30? 30 minus 19.
11. Oh, 30. 11.
Okay, 11. 1 milliliter was my indicator. So I put in 10 milliliters of acid to start off with. Please, somebody write that down so we don't forget, because we have to know how much acid we added.
Got it.
10 milliliters of acid. I've delivered 19 milliliters of base, and now I've come to a pH of 0.307, or 3.07. So 19 times 2. What's 19 times 2?
38.
38. So if our endpoint is at 38 milliliters, then we know it's methylmalonic acid. Methylmalonic acid. All right.
How do we know it? Sorry.
Because, now we're going to go back to this screen, so remind me to go back to it. Because when we get to the endpoint, that's going to be twice as far as the pKa. The pKa is the pH when half of your titration is complete. Half of your
dissociated.
HA is dissociated. That's right. The pKa is the pH where half of it is dissociated. So if we have reached the point of half dissociation at 19 milliliters, then what that would mean is that the endpoint would be at 38 milliliters. So if we get to 38 milliliters and we get the endpoint, then we know it was methylmalonic acid. And Samantha has written down 19, or actually, yeah, you can write down 19, right, for methylmalonic acid, Samantha?
Yes.
And also write down 28, because that would be the endpoint, the hypothesized endpoint. Now we're going to go to the next one, which is 3.94. So I will add another milliliter until we get to 3.94. Keep adding, keep adding, keep adding. Can you guys see my thing? You can't see my thing, can you? Or can you?
I can zoom.
I can see it.
Okay, great. 3.29, 3.31, 3.32, 3.34, 3.8. Okay. I need more base, right? Can you see it?
Yes.
I ran out.
Mhm.
So we're at 3.47. Samantha, I need you to write down 50 mils because we've already had 50 mils and we can't forget how much of that stuff we added, right?
Yes.
So I'm going to add a 50 milliliters back in again. We're going to, oops, 2 more milliliters. Or I'm out, huh? Bad bottle. Sodium hydroxide, 10 millimolar. Where is it at? There it is. All right. 2 more mils. Okay. Back to business. Ready?
Mhm.
One milliliter
Ready.
at a time. I'm adding 3.48, 3.49, 3.5. Whoops. Ah. At 16, was it? We were at, oh no, we haven't got there yet. Or,
Not yet.
not yet, okay. 3.94. Whoops. 51. So we're at 101 now. This time I'm only going to add 50. 50.
Mhm.
There we go. Okay, good. Okay, so I've added 101 mils, right?
Yes.
102, 3.79. Whoops, didn't write it down. 102, 3.8, 103, 3.8 as well. 104, 3.81, 106. Wow, see how the pH is slowing way down, the pH change?
Yes.
It's acting like this is a strong buffer zone because when you add the pH or add the base, the pH isn't changing much. So there we are. 35, a total of 135, is that right?
Yes.
Yeah. Yes.
135, and
Oh.
that would mean that we're, if, what, 270
Oh.
milliliters. If we end at 270 milliliters, then the pKa, the unknown acid is diphenylacetic acid. I wonder if we need to have more concentrated base. pH, the 1 or the 0.01 molar stuff isn't cutting it very well. Okay, so the next one to come up would be 4.69 crotonic acid. Okay, so do you have those values written down, Samantha?
I do.
Okay, so you have 135 written down for 1, right?
Yes.
And 270 for its predicted endpoint, right?
Yes.
Okay. So let's keep going here. I did it again. I'm just impatient. 1 milliliter. Let's pour in there. 1 more milliliter. Oh, he left it. No.
I have a question.
Yeah.
How do we know when to stop pouring out the base inside the 250 ml flask?
Well,
Should
as
we
soon as
just,
the solution becomes basic, like if it becomes higher than 7, right? Then that shows us that we've run out of acid and we have basic conditions.
Oh,
Does that make sense?
oh, over here on the left side.
Yeah, over here,
The
the pH.
okay.
If we click right here, it tells us what the current pH is. We're currently at pH 4. I think we need a higher concentration of acid. I think that's what we need. I think we need a higher concentration of acid. So maybe we should start over with a new Erlenmeyer flask. New Erlenmeyer flask. This time, maybe I'm only going to put 1 milliliter of my stuff in there. Is that okay? 1 milliliter of my Erlenmeyer flask. I'll put in a point, 1 milliliter of this indicator as well. Where are we at with this stuff? How much do we have of this stuff? This one I'm going to get rid of. How much do I have? I don't have 40 mils. I'll put in as much as I have. That was 36. Then I'll get some more sodium hydroxide. Four more milliliters there. Okay. So now I got, instead of 10 milliliters, I only have 1 milliliter in there, right?
Yes.
Yes.
So, same game. Let's try to start over here, and let's use less this time. So, what was the volume that it required to reach 3.07 last time?
3.0, that was 19 milliliters.
19 milliliters. So it should only take 1.9 this time because there's only 1/10 of that stuff, right?
Yes.
Does that make sense? So I'm going to just verify that by putting 0.1 in there, right? And I'm going to do that. Watch my pH as I go. Yeah, see there, 1.9. Now we know it's not methylmalonic acid, right? How do we know that?
Because the methylmalonic. Oh no, because it's 19. It always starts with 19, and the end point is 38.
That's right. And last time we went way past that, right?
Okay.
So we know it's not that. So now let's go until we get to 3.94. What was the volume for 3.94 again?
135.
135. So that's 13.5 of this stuff. So let me just add, well, I'll add 0.1 to get to 2. And then we'll just add 1 milliliter till we get to 13. And we'll just double check that we don't get above. So how much did we say we have to go to? 13?
Yes.
Yeah, it's right. 12. 13.5, is that what we said?
Yes.
Yes.
So there's 13. So now I'll just do 0.1. Uh, 13.5, right. All right, so our endpoint here would be 27, perhaps. So I'm just going to keep adding until we get to, so 27. You want to jot that down, somebody? 27. And I'm going to keep adding until I get to 4.69. We're at 4.
Okay. This is for crotonic acid. Okay, I'll get it.
Yeah. So I'm going to just add a milliliter at a time there. 4.1, 4.14. So did we pass our Where did we say it would be for diphenylacetic acid?
3.94.
What's that?
3.94.
Oh, but the volume.
Oh, the volume. The endpoint is 207.
So 20.7, right?
Yes.
So it's not diphenylacetic acid either, because we're already at 21. Is that true, Samantha? Is that what you had as well?
Yes.
Okay. So it's not methylmalonic. It's not diphenylacetic. The only two it could be at this point is crotonic or, well, I guess alloxonic or methyl M aminobenzoic. So let's keep adding. The next pKa is 4.69. Wow, we are adding a lot of acid. So at about 45.5, we got to crotonic acid, pKa. 45.5, so that would be 90. I'm going to jot this down here in mine as well. So that's crotonic acid, is that right?
Yes.
45.5. Oh, 40.5.
45, so it's 90 milliliters, right? Okay. So for crotonic acid, all right. Okay, let's see where we're at now. Okay, so 47, 48, 49, 50. I'm going to put some more of this stuff in. 50 more milliliters. $51. 52, 53, 54. What's the next pKa? 5.10?
Yes.
5.10, yes. For methyl aminobenzoic.
Okay, so it looks like it was about 15.5 or 65.5. 65.5. That would be 130, right? Is that right? 65, 131. For methylbenzoic, what was it again?
Methyl M aminobenzoic.
Methyl M aminobenzoic acid. Okay. Whoops. That's not the one. So, $6.64 is the last one. Who is changing pretty fast now. I don't think we're going to get to 6.64. I think that we're getting close to an end here. Yeah, we're almost done. So, which one is it? If we're almost done now, which one would it have been? Any of them? What is our volume? Oh, we're about 90 milliliters, right?
Yes.
Yes.
We're about 90 milliliters. So it must be crotonic acid. So we're going to try to add it nice and carefully now because we can see the pH is rising. We're going to try to add it nice and carefully at 0.1 milliliter increments. Okay? And wait for our pH, or our indicator to change colors, or our pH to be about 9. Yeah. So did I put indicator in here? Yeah, I did, right? It looks like we're there already, though, but I'll do one more. Did I put in? Oh, I didn't put much indicator in. That was the problem. I need to put more indicator in. Oh, that wasn't the problem. So it's only going to turn that pink for me, huh? So it was about 42 milliliters, or 92 milliliters, right?
Yes.
So what acid was it then?
Tonic?
Crotonic acid. Crotonic acid. Okay. So crotonic acid. Now we just need to know the concentration. And what was the pKa? What volume was it with the pKa?
4.62. Oh, for
crotonic acid, was it 4.5 or 45 milliliters?
4.69.
What's that?
Oh, the pKa is 4.69.
Uh-huh. But it was at 45 milliliters where we reached that, is that right?
Yes. 45.
Okay. What's that? Say that again. 4 point what?
Oh, 45.
45. All right. So that means it is going to require 90 milliliters to consume all the crotonic acid. Okay. So all we have to do is our calculation. We want to know the concentration of acid. We want to know the moles per liter, right? It took what volume? 90 mils?
Yes, for the crotonic.
Yeah, I should say 0.09 liters of our base, right? True? Is everybody online?
Yes.
Okay.
Yes.
Yes.
And now we go for moles of, liters of sodium hydroxide, right? To what?
To moles of
To moles of sodium hydroxide, right?
yes.
So we got moles of sodium hydroxide here, moles of sodium hydroxide to moles of my acid here. If you guys want to fill that out, that would be great. And then moles of our acid is going to be up here, and then we need just liters of acid down here, right? And the liters of acid, we just added 1 milliliter, right? Instead of 10. Whoops.
Yes.
Oh, okay. There you go. I didn't see the in presentation.
So
This is where the moles.
So we got liters going to liters to moles of NaOH, moles of NaOH to moles of our acid. And this is our volume of our acid, which was 0.001 liters of our acid, which we'll call just HA for ease. Okay. The moles of sodium hydroxide per liter. Do you know what that is, Samantha?
That was
What's our concentration of sodium hydroxide? Do you remember?
it 1?
It
1 or
was,
10?
it was 0.01, right?
Yes. Yes.
0.01 moles of sodium hydroxide per liter.
Where did we get?
Where do we get what?
The moles of sodium hydroxide.
Where do we get
Oh,
that?
no, where did you get that? 0.01. Rather.
Let's go back to our thing here. Can you see it?
Yes.
Yes.
So it said right here, this is the concentration of our sodium hydroxide, 0.01. See that?
Yes.
So if we had chosen something else, it would have been something else. But now, why isn't this turning more pink? Oh, there we go. Yeah, let's put a lot in, make it lots of pink. Good. Like that better. Okay. Back to our calculation. What do we got? Anybody do it yet?
Oh. Not yet.
0.9.
0.9. Okay. 0.9 molar, huh? Okay, so, oh God, I almost went on without you. Let's see here. Let's share the board. So what did we say the acid was? Crotonic acid?
Yes.
And three significant figures, 0.900. Is that true?
Yes.
It was right at 45. Are we lucky? Oh, we're not lucky. So this is probably the problem. The problem is probably, so we have another chance, we have a couple more chances. You have the correct acid, but your concentration is wrong. Try working on smaller additions. Yeah. So there, and we're probably slightly off here. Slightly off. So what we're going to do this time is we'll repeat it with another Erlenmeyer flask. Another Erlenmeyer flask here. And we'll put in, this time I'm going to put in, let's see, how many milliliters did it take for that titration again? 90 milliliters?
Yes.
If we put in 1 milliliter and it took 90 milliliters last time, right? 90 is too much, so let's put in a half a milliliter. Is that okay?
Yeah, okay.
Yes.
So I'm going to put in 0.5. So this time the titration should be what?
45.
45. I'm going to put in a heap of phenolphthalein so we get a good, strong color change for us. How much do I have in my burette now? I'm going to need more. I'm going to need 42.123. Let's bring it up to the top. Okay. Should be 45, right?
Yes.
So I'll go to 35. Go to 40. Go to 44. Now I'll do 0.05 instead of 0.1. All right, ready? Let's be
Ready.
nice and careful here. There it is. Right there. Okay? So 45 point what?
7.
45.5675. 45.75, right?
Yes.
I'd say so.
Okay, so 45.75. How does that change our calculation here? So you put 0.04575 this time, right? 0.04575 and times it by the 0.01. But this time we don't divide it by the 0.001, but we divide it by what?
Because I think they still use the zero. Oh no.
What's that?
Oh no.
Because I didn't add 1 milliliter last time, right? Remember?
You added half a milliliter this time.
Right. So divide by 0.0005. So this is going to be 0.0005. This one is 0. What did we say? 0. What was it?
For
Did we
I don't
forget?
fully remember.
54575.
4575.
Yes.
4575. That's a 75. Okay, so 0.04575 times 0.01 divided by 0.001. Right?
Yes.
Anybody get an answer? Did anybody get an answer?
I got 83, but I don't think that's right.
God. Here's mine. 0.0915.
0.0 or 0.915?
0.0915.
Okay. That's slightly different than what we had last time, right?
There we go. Yeah, I got the same thing now.
Okay. So let's try it then. Wait, let me do that calculation myself really quick here, just to make sure. Okay, 0.04575 times 0.01 divided by 0.0005. I'm getting 0.915.
That's what I got.
Not 0.0915, right?
Correct.
Oh, I forgot to add another zero for. That's why.
Did we do the calculation wrong last time? We had 0.09 times 0.01 divided by 0.0005. Oh no, not divided by 0.0005, divided by 0.001. Let's try that again. 0.09, that was our 90 milliliters, times 0.01 divided by 0.001. Yeah. So last time our calculation should have been 0.9. And this time, what is it?
0.915.
915 or 0.911?
0.915.
Okay. We ready to try it?
Yes.
Here we go.
Crotonic acid.
Yeah, we still got the crotonic acid up there. We got it! Hooray! All right. Okay. So, we've got 3 done, right?
Yes.
And I think it's probably a good time to stop, or do you want to try to do one more? It's
So
up to
the
you.
okay.
What's that?
I was just wondering, so like the pattern should be like this, right? Like the procedure, same thing with base.
Yeah, same thing with the base, and you might have to look some stuff up on YouTube or internet or YouTube to try to understand some concepts, and there might be some slight changes, but pretty much the same idea. I mean, following. There's a few things that I think you're gonna have to learn with all of them. Just kind of looking up videos in YouTube, like videos or YouTube, and finding stuff online. But that's all right. We got to learn something.
Okay.
Okay. Do you want to try another one, or do you want to call it quits for today?
I was just wondering why, on my end, when I just tried it, or should we supposed to have different problems?
Yeah. Each time you refresh it, it's a different one.
Okay.
So next,
Because my
yeah. Go ahead.
sorry.
Go ahead.
As in mine, I try to put in the answer too, but it says it's incorrect.
Yeah. You'll have to
I
follow
think.
follow that pattern for
Okay.
for your own sample. Right,
Okay.
Samantha? Does that make sense?
Yes, it makes sense.
So we can meet again on next Thursday and go over some more of these if you want to. But I think it would be good for you guys to first you got to finish up these ones, these 3 that we did today, and then you got 2 more after that if you did Lab 11, right? If you didn't do Lab 11, or if you'd prefer to just try to do all 7 of these, then you can do that. But yeah.
Sounds
Are
good.
the recordings we have are listed in? Is
Say
it?
that again.
Oh, are the files or the recordings for these videos saved somewhere in the canvas?
Yes, there. You can still see my screen, correct?
Yes.
So right here, let's see. Did we have a? Was this the
Lab
first one we did? Did we have a video? I can't remember if we did another recording. Did we? You guys, did we do another class last week? What did we do last week? Oh, we didn't meet last week. That's right.
Holiday. It was a holiday last.
Yeah, it was a holiday. So this is the first one. But yeah, I'll put a link to that video right here on this homepage.
Oh, okay.
It'll take a while to download to YouTube, but I'm recording right now, so this whole thing will be there.
Okay.
I can
And-
actually, because the section 2 lab went over this already. So I could give you this link right here. This is the video that the second section did. Does that make sense?
Yes.
We only did the first 2. We didn't get to the third one. But I will add that on here. It will video
So is it correct? We did 2 mini exercises today.
what's that?
Today we did 2 mini lab exercises.
We did 3.
Oh, okay. I missed the first one.
Yeah, but this one here is just the video from a different section where we did the first 2. I'm just giving this to you now so that if you're anxious and want to do it before I have the other ones uploaded, this video uploaded, you could have access to it right now, right?
Yes.
Okay, so there is, whoops, got one more thing here. Why didn't it? Huh. There we go. So this video here is what we did last time.
Solid. That's all I
As-
know.
Okay, it's a solid.
Oh, okay. No, I've seen that.
Let's see. Oops, you guys can't see my screen yet. Now you can, correct? Yep, this one we did the acid base titration and the silver chloride one. All right. Do you guys, what else do you want to do? Anything else, or are we done? I mean, you have me till 6 o'clock for sure if you want to keep working on one of them. Or should we take a break?
I gotta go for a break. I'll try to do it on my own and then.
Sure. How about you,
Yeah.
Samantha? Are your brain fried too?
I'll do the same thing. But thank you so much.
You're welcome.
I feel like I understand how to work the program now.
Okay, good. All right, we'll see you guys hopefully in class and also next lab time if we ever want to, again, we have another week, 2 more weeks before these things are really due, right? So for sure we'll meet next week and we'll try to walk through a couple if you still have questions. I would try to become as familiar as possible with the other ones so that you can understand what's going on. All right?
Okay. Thank you
Sounds
very
good.
much, brother Scott.
Okay, see you later. Bye-bye.
Thank you.
Bye-bye.
Bye.
Bye, you're welcome.